Okay, it is clear now that an arbitrary payload later deserialized on server side can be stored into the view state. However, the view state is still encrypted and protected with a message authentication code appended to it. To understand if there is any possibility for abuse, we must check the crypt options which come by default with the Apache MyFaces configuration, as developers adopting the framework normally do not pay attention to them and tend instead to use the standard settings. The first option to look at is this one. It indicates the encryption algorithm used to encrypt the view state. The algorithm utilized by default is DES, Data Encryption Standard, providing an effective key length of just 56 bits. DES is considered deprecated since 1999. The minimum recommended protection level today is at least AES with a 128 bits long key. It means DES is easy to crack and absolutely a bad choice to protect view state strings. This is good news for the attacker. Then there is this other option, which defines the mode of operation and the padding scheme used along with the encryption algorithm. The default values are ECB as a mode of operation and PKCS 5 as a padding scheme. Let's explain these two things. This is a so-called block-based encryption algorithm because a plain text message is first divided in blocks of the same size before being encrypted. Specifically, this works with 8 bytes long data blocks. A mode of operation dictates how these data blocks have to be chained together during encryption. ECB is a weak mode of operation because two blocks of data containing the same plain text, once encrypted, will produce in output exactly the same ciphertext. A padding scheme is instead the mechanism to keep a block of data aligned to the 8 bytes boundary. For example, let's assume the last block of data of a message contains just 6 bytes. This block is padded with 2 additional bytes before being encrypted in order to respect the 8 bytes boundary. But what value the 2 padding bytes must be set to? According to PKCS 5 scheme, as there are just 2 bytes of padding, these have to be set both to the value 0x02. If there had been the need of 3 padding bytes instead, their value would have been set to 0x03 and so on and so forth. An interesting case occurs when the last byte contains only user data, as seen in this slide. One would expect the message to be encrypted and sent with the last block as is. However, how would the recipient interpret it if last decrypted byte was set to the value 0x01? Would that byte be considered regular user data or just padding? The recipient could not simply distinguish between the two cases because 0x01 is indeed a valid value as both user data and padding. That is why when the last block contains only user data, A, B, C, D, E, F, G, H in the slide showed right now, a full block of padding with each byte set to 0x08 is appended to it. Then the message can be encrypted. You can learn more about PKCS 5 from this link if you like. Between the crypto settings of Apache MyFaces, there is also an option indicating the algorithm used to calculate the message authentication code, protecting the view state from tampering. The default value is HMAC SHA-1. Now we have all the pieces to attempt an attack against a web application developed with the MyFaces framework that makes use of encrypted view state values. Let's see step to step how to proceed. As an attacker, we initially retrieve the view state value from the web application. It is base64 encoded, therefore we decode it. After decoding, we split up the output in two parts, the disencrypted view state and the message authentication code calculated over it. As by default Apache MyFaces uses HMAC SHA-1 algorithm, the hash generated is always 20 bytes long. So the last 20 bytes of the base64 decoded view state will be the message authentication code, with the rest being instead the encrypted part of the view state. Now the attacker decrypts the view state. But how can this be done if the encryption secret key is unknown? Well, as we said, this is an obsolete encryption algorithm. Few computational resources are needed to brute force a DES key even with commodity hardware. Also, the brute force attack is totally doable offline because all the attacker needs is just to retrieve from the server a view state value only once. No other HTTP request is required for this step. Additionally, the attacker performs the brute force only on the first block of data, which is 8 bytes long, not the entire view state. As with MyFaces, the content of this block is well known and always decrypts to the same value. Basically, the encryption key is found when the targeted encrypted block will decrypt to the byte sequence ACED 0005 7572 0013, with ACED 0005 indicating the presence of a Java serialized object in there. Also, at the end of the decrypted view state are clearly visible the PKCS 5 padding bytes applied to the message. Now that the disencryption key is retrieved, the attacker can pick up a gadget chain with WISO serial, for example, and replace the original object in the view state with its malicious payload. Of course, the malicious payload will have to be padded properly by following the PKCS scheme, otherwise the message will be invalidated. The attacker now encrypts the view state containing the malicious payload using the same encryption key he has managed to brute force few steps ago. With the oldest versions of MyFaces, this was enough to exploit the arbitrary deserialization vulnerability. But as the most recent versions of the framework protects the view state by appending a message authentication code, this is not possible anymore unless attacker finds a way to discover the HMAC key too. The default behavior of MyFaces is to generate a random HMAC key if one is not provided. And this key changes every time the service is restarted. However, a very common mistake is to use the vocabulary word as HMAC key, or even worse, to use the same value for the encryption and the HMAC key, which is a totally insecure approach. Because such bad practices are widespread, in many cases the HMAC key can be brute forced locally too, just like done for the DES encryption key.